السلام عليكم.
Assalamu alaikum. There is no sound, Doctor.
You hear me now? Hello?
Yes, we can now. Yes.
Right, okay. We talk about the spectral radius of a matrix, and this is a definition. Spectral radius of a matrix is the maximum value of the eigenvalue of a matrix, and this is, we discussed last time how to find out the eigenvalue. We have to take the determinant of A minus lambda I equal to 0, and then that will give you the value of the lambda we have here now. So we need only this information, and that I give you the sufficient condition, which I told you one of the third one and the best one, the convergence condition for the iterative method. You remember we already discussed two. One is if your system is STD, then the iterative method converge. The second one is if the norm of the T of the iterative method is less than 1, iterative method also converge. And this is the third one. And the third one is what? If the spectral radius of the T of the iterative method is less than 1, then it is also 100% guarantee the method is converged. So this is true for the both side, reverse also true. If it is converged, this happen. If this happen, definitely the method will be converged. The other two conditions we discussed, they are sufficient. Sufficient means true only one side, reverse we don't know. Maybe, maybe not. Then we discuss, I give this condition here. You remember that one, the last things we finish, I discuss also convergent matrix. If the spectral radius of a matrix is less than 1, then we say the matrix is convergent. Otherwise, we say divergent matrix, which I give the example last time, this one here. And this is the last thing we finish here. And I give you here that If the matrix is a non-symmetric, then A2 norm we can find out with the help of this formula. And the second condition, the spectral radius of A always less than equal to norm of A, and any norm, A2 norm or L infinity norm, you can use that one. And this is the condition for the symmetric matrix. If the matrix is symmetric, then A2 norm is simply the value of what? The spectral area. This is the things we finished last time, please. And we remember, here we have some problem, because if you remember that one last lecture, I told you the trace of this one is what? The trace of this one is a 3, because trace mean sum of the diagonal element. The trace of this one is, and I told you the trace of A and the sum of the eigenvalue of A must be the same. And here by mistake it was 3 last time. I corrected in Alhamdulillah. So things is now is okay now. Now let's come to the last method, iterative method, which we call successive over relaxation method. And the successive over relaxation method is what? It is a modification of the Gauss-Seidel methods. And in the Gauss-Seidel method, I told you Gauss-Seidel method may converge, may diverge. But if converge, it is converged faster than Jacobi method. But if you talk alone Gauss-Seidel method also converges slow. So to make it faster convergence, we make small modification in the Gauss-Seidel method, and then we have a new formula, and that formula we call successive over relaxation method, or in the shortcut we call SOR, the methods we have here now. And this is a formula, the SOR methods we have, please. If you remember that one here, we introduce a parameter which we call omega here. And that parameter we call the relaxation parameter. And this is, if you can look this formula, if we have the value of omega or W, whatever you call it, if the value of the omega is equal to 1, then this SOR formula become exactly the same Gauss-Seidel method, because when it become 1, this becomes 0, and this become 1 over AIA, and this is the formula of the Gauss-Seidel methods here. So the modification we can make it here now is we introduce in the Gauss-Seidel formula a relaxation parameter, which we call omega here. And the range of omega is this one. Omega. The range of omega is this one. Your SOR method will converge also if this condition say 0, omega range is between 0 and 2, but of course not 1, because if your omega is 1, it become the simple Gauss-Seidel methods we have here now. Now we can have we divided this, the big range 0 to 2 into 2 parts. The first part is 0, omega to 1. The other one we call 1, omega to 2. Now, what is this range mean? We can have the over relaxation method. We have a 2 shape. One shape we call under relaxation, right? Under relaxation method. And under relaxation method mean if you use this formula and you use the value of omega is between 0 and 1, then we call it under relaxation method. And if you use this range, this is called over relaxation methods we have here now. Now, what are the basic conditions for this one? If you remember that one as in the case of when we start the first iterative method, and we have the Jacobi method, and then we check Jacobi method for one of the example we discussed, and we check Jacobi method converge very slow. I think it took 16 iteration to get the accuracy 10-6, if you remember. Then which mean it is a very slow, then we make small modification to make it faster. And that small modification what we make in the Jacobi formula, your Jacobi formula change, and we call it a new formula, which we call Gauss-Seidel method. But this small modification will do only one job. He can make slow converge to faster, but it will not give you guarantee that if your Jacobi method is diverge, it make it guarantee converge. No, this is not. The modification does not give you the guarantee that from diverge to converge. Maybe, maybe not, but no guarantee. But one thing is guaranteed, if it is slow converge, it make it faster here. Now, what we did here, in the case of the third iterative method, we make small modification in the Gauss-Seidel method to make it faster. And this modification which we make in the Gauss-Seidel method, they give you the both condition. If it is converge, slow, Gauss-Seidel converge slow, it make it faster. And the second condition, if the Gauss-Seidel method diverge, this will make it faster here. This is a good point of the relaxation method. Relaxation method. And what is the condition for? The condition, if you choose the value of W between 0 and 1, what he will do, which we call under relaxation method, this we will use the condition when Gauss-Seidel method diverge, this condition will make it converge. And this second condition, we choose omega value between 1 and 2, and this will make what? When Gauss-Seidel converge slow, it make it the faster here. So this is, we have the two benefits here in the case of the SOR method, relaxation method. But the problem is what? If we use this condition, we have to choose the value of omega by ourselves. There is no proper formula for this one. And if we choose some value, if we are lucky, maybe we get the diverge. Otherwise, we have to retry again and again because we have no formula, some optimal formula for in that case here. So therefore, generally, we will never discuss under relaxation method. In our case, we discuss only one case, which we call over relaxation method or successive over relaxation method or SOR method, where when the Gauss-Seidel method converge, it make it faster. This is a basic theory behind the SOR method, the modification of the Gauss-Seidel method. And that modification we make in the form of omega. Omega is called the parameter, relaxation parameter. And the range of omega is between 0 and 2. If the range between 0 and 1, we call under relaxation method, which we will not generally discuss here. And we will discuss only this case here, which we call over relaxation method. That means here we have a optimal rule, optimal formula to find the best value of omega in this range to work with the SOR method, because SOR method, if you look for the formula, SOR method need the value of the omega. This formula SOR and this one exactly the same here, only the way of writing is different, otherwise they are the same one we have here. And this is a formula you have to remember, because you already know what is the formula of T for the case of Jacobi, what is the formula of T for the case of Gauss-Seidel. Now here you have to remember the formula of T for omega for SOR matrix and the C constant for SOR matrix. Slightly lengthy formula, but you have no other choice. You have to memorize it here. And D, you know the diagonal part of the given system. L is a lower part of the system and U is the upper part of the system. And omega you have to calculate. Either teacher gave you the value of omega or you have to use the formula which I will discuss inshallah. It will give you how to calculate the value of omega. This is I mentioned here that the range for omega is 0 to 2. But if you choose omega equal to 1, then your SOR becomes simply the Gauss-Seidel method. So your SOR become simply the Gauss-Seidel method. And therefore, as I mentioned also, same thing I repeat, if the range of omega between 0 and 1, and that procedure is called under relaxation method. And why we use under relaxation method? We use under relaxation method, which can be used to obtain convergence of some system that are not converged by the Gauss-Seidel methods here. But as I told you, which is we have to choose different value of omega by ourselves, and then if we are lucky, someone value of omega give us a very good condition for the convergence. Otherwise, we have to continue to try on. The second choice is the best choice we have that we will use inshallah. And it will be that omega between 1 and 2. And this procedure is called over-relaxation method. And that we can use to accelerate the convergence of the system of the convergent Gauss-Seidel method. Mean when your Gauss-Seidel make converge, it make it more faster than things here. And generally, we use SOR method in our case here. This is the example I gave last time in the exam, in the midterm exam. And I say here that find the L infinity norm of SOR iteration matrix TW, where omega is given by the teacher 1.005. So it's mean you only have to remember this formula, if not problem. So you have to memorize this one. You know the D is a diagonal part, 5, 0, 0, 10. And this is given here. D is this one. U is the upper part of the matrix, and L is a lower part of the matrix here. And then you use the formula, this one here, use calculator. And inshallah, you will end with this. This is your SOR iteration matrix, which we call TW here. And then he say, find the L infinity norm. And you already know what is the meaning of L infinity norm. L infinity norm mean the maximum of the row in the absolute sense. So what is the first row? If you can see here, the first row is 206. And what is the second row is 00157. And of course, what is the maximum value? Maximum value is this. That's the way you have to be. As I told you, I give this problem in the exam last time here. Any question you have up to now, please?
think it's clear, Doctor.
Is okay, good. Now let's, I use a example here and I say, solve this system with the using accuracy 10 minus 4 here. And if you can see here, you can see, is this one STD or not? Your system is STD or not?
Not.
Not.
Not the system.
Is not STD. And you know, as I told you, if your system is STD, it is 100% guarantee the iterative method converge. But if it is not STD, then we don't know, maybe converge, maybe the diverge. So what I did, this method, this system, I use two methods, SOR and the Gauss-Seidel method. And when I use the Gauss-Seidel method, I got this approximation, which is very strange. You see the big difference between them, changing negative to positive, positive to negative. It means something is wrong, and the wrong is what? Jacobi, a Gauss-Seidel method for this method is diverge. But we use under relaxation method to make it converge, and that I use here. I choose the value of omega, and for this value of omega, its method is converge. It converge, but it converge very, very slow. Therefore, as I told you, the under relaxation method is not suitable to discuss here, because first of all, we have no formula to how to use this value, and we have to head and trail like that one. We have to pick and choose. If work, good. If not, then try another number, which is a waste of time here. But I just give you the idea, because I told you if the range of W is between 0 and 1, this will give you the method where the system for the system where Gauss-Seidel method can diverge, it make it converge here. Slow, this is no guarantee here. And that I give the system here in the form of, this is in the form of Gauss-Seidel formula for the given system, and I give this value. And this is, I use the SOR formula with this value of omega you put here, and this formula, inshallah, you will get this approximation, which I show you in the table we have here now. Now we have another example, which is also you can see here, your Gauss-Seidel method. This is not STD, but still your Gauss-Seidel method is converge. For this system, Gauss-Seidel method converge, and it converge how many iteration? 36 iteration with the accuracy 10 minus 6. But we use SOR method. SOR method, when we use the value of omega is 1.27, SOR method converge. But it took 16, too much here, but much better than these Gauss-Seidel methods we have here now. This is the things we have here now. This is, I give you the condition here, the theorem, that SOR method is always remember that one, the spectral radius of TW, the SOR iteration matrix, always equal to omega minus 1, but with this condition. If this condition, then this happen, and the condition is what? If the diagonal element of the matrix are non-zero, not a single element in the given A matrix is 0. If it is 0, then we cannot use this formula. If the diagonal element of the given matrix is a non-zero, then this happen, and this happen mean omega range is between 0 and the 2 we have here. Now this is the good theorems we have to. Generally we use in the exam this one. Number one, if A is a positive definite matrix, you already know what do you mean by positive definite matrix. If A is a positive definite matrix and the range of W is between 0 and 2, then we say SOR method always converge for any initial approximation we choose here. But the theorem which we are interested, which is a very good from examination point of view, it is a theorem number 1.36. This is the best theorem we have here now, and that will help a lot the problem given in the exam we have here now. And what is this one? If A is a positive definite and tridiagonal matrix, you know what you mean by the tridiagonal matrix, please? Any student? What is the meaning of the tridiagonal? Any student? You will have A is equal to what? Let's say 1, 2, 3. And then we have 4, 5, 6, 7, 8, and 9. This is your simple matrix here. If a matrix where the diagonal element and one upper part and one lower part in the diagonal position not equal to 0, the rest 0 is called the tridiagonal. So this means if this is what? If this is 0 and this is 0, then we call it is a tridiagonal matrix. Tridiagonal matrix mean all the diagonal element and one upper diagonal like this one, 2 and 6 and 4 and 8 is the lower. This should not be equal to 0. Rest, how many is the size of the matrix? 2 million by 2 million or whatever. Only this two condition is satisfied, then we call it is a tridiagonal matrix. So if A, yes. Yes, please. Yes, any question? Hello?
Yes, doctor, no question.
No question, right. You understand this one is there? If the diagonal part and one upper diagonal part and one lower diagonal part, only these 3 diagonal parts not equal to 0, the rest must be 0. What is the size of the matrix? We don't care. 3 by 3 is a minimum case in the case of the tridiagonal matrix, and 4 by 4 or whatever. We call it is a tridiagonal matrix. And you already know the idea of the positive definite matrix here. So if your A is a positive definite and tridiagonal matrix, then remember this one, please. This is a very good condition. The spectral radius of Jacobi iteration matrix always equal to the spectral radius of the Jacobi iteration matrix square, and both must be less than 1. And you remember I told you, if the spectral radius of the iteration matrix of the iterative method is less than 1, it is 100% guarantee the method will converge. And with the also this condition, positive definite and tridiagonal, we can find the optimal value of the omega for given system. And we have the formula is what? 2 taqsim by 1 plus square root of 1 minus spectral radius of Tj square. And that will give you the omega, because generally in exam teacher never give you the value of omega. You have to calculate by yourself. And the range I told you, the omega is between 1 and the 2 we have here now. And also the third condition we have here now, the spectral radius of T omega always omega minus 1. So this is a very, very good theorem from examination of point of view, and no 90% chance or 80% chance, it is 100% chance. This theorem you have to use in the exam here. Teacher must give you the example, which you have to use it here now. Right. This is the example I give in the exam, please. He say, define. Now let's say here, if we can say the simple problem like that one here. He say here, only one choice, omega. He say, find the optimal choice for the relaxation parameter or factor, which we call omega, for using this matrix here. Let's in the exam. My question is this one. Show that for the system, and system is what? X is equal to the B, where A equal to this one. Teacher not give you the B, he give you only A. Show that for the system A equal to B, where B, A is given. Show that SOR method converges. SOR method converges faster. SOR method converges faster than Gauss-Seidel and Jacobi the method. How can you show this one, please? How can you show this one? Or let's say I put in other way, the question is, for this system where A is equal to this one, check SOR method, Gauss-Seidel method, and Jacobi method converge. All three are converge, and then show SOR is converge faster than Seidel, and Seidel is faster than the Jacobi methods. How can you do this one, please, here? What is the condition of the convergence?
I calculate Tj and Tg.
No. First of all, here, what is the mathematically you have to show? Then you do the process, right? Do the procedure. Well, you should know the formula which you have to show. You have to show the spectral radius, right? Which we call rho, right? We call rho, I call rho here, spectral radius. Rho of T omega is less than rho of Tg, and this is less than rho of Tj. This is you have to show. This you have to show first, please. Smaller the, because this should be what? All that should be less than the 1. And then smaller the value of row, faster the convergence. Yes, please. How can you do this one here now? It's mean you can see your this matrix is what? Your this matrix is positive definite. Positive definite means symmetric also. This is symmetric and tridiagonal. And the tridiagonal I just discussed here. The diagonal part, one upper diagonal part and one lower diagonal part should not be 0, but other should be equal to 0. Can you hear me, please? Is okay now?
Yes.
It's okay now.
Okay, alhamdulillah. There's some problem with the net here now. Now, what we have to do, we use this condition, the theorem 1.36. And as I told you, this is 100% guarantee this problem will come in the exam here. So no choice, other choice we can have here now. So what we have to do, we have to say, we have to find out first thing is what? We need to find out the Jacobi iteration matrix. And after finding the Jacobi iteration matrix, what we have to do, we have to find its spectral radius. And how to find its spectral radius, please? You remember I give you the formula, determinant of the matrix, and the matrix we are using is Jacobi minus lambda into I determinant. This should be equal to what?
0.
0. And then we find the largest element of this case, and that will be the spectral radius of Tj. When you find spectral radius of Tj, no need to find Tg, because you use just this formula. You square that spectral radius of Tj. This will give you what? The spectral radius of Tg. And then you use this formula because you need spectral radius of Tj here. You find the optimal choice of the W. And then you use this formula. You know the optimal value of omega from here. And take the minus between them, and that will give you the spectral radius of T omega. You understand my point, please? That's a simple way to do. Only in this question, we have to calculate the Tg. And that formula you already know. What is the Tj formula? If you remember, Tj formula is what? Minus D inverse into L plus U we have here now. Let's do here now. You find the Tj inverse by using the formula. I directly give the value of Tj here now, please. And this is a value you get. And I told you, please, for any system, the diagonal element of Tj always 0. If it is not coming 0, then it's mean something wrong with your calculation. You have to use the wrong formula, which is correct one is this one here. So we have this one. And also I give you the shortcut. Remember, I give you the shortcut before also, how to find Tj, please. I give you the shortcut, please. Is any student remember? No need to use this formula. No need to use this formula to find Tj. You can have a shortcut. No, you don't remember. Any one of that one is not remembered here. And the shortcut formula is what? You taqsim your diagonal in each row. And then make your diagonal 0. So diagonal is 0, 0. This is the first thing. You taqsim your diagonal. So what you have? -1/2. If here is a negative, it should be here positive.
Positive.
It is a 0, so 0 is a 0. Here, you taksim by second row by 2 again. You have -half, so it should be opposite sign. -half should be opposite sign, and the same thing you can have. This is directly you can approach to the Jacobi iteration matrix without using its original formula here. Now you have to find out the spectroradius of the Jacobi iteration matrix, and for this you have to use this formula, the determinant of Tj. Here a student confused in exam, they use in place of Tj, they use a, no, we don't care about a, we care about Tj, Tg, and T omega. And when we find this omega, the determinant, and alhamdulillah, we will get this one. And this is the value of this one. And then we take the maximum value. So what is the spectral radius of Tj? Is this one, and spectral radius of Tj should be less than 1 because we have to show the Jacobi method converge. Yes, it is less than 1 converge. So when you have this choice here, and you can find out the optimal value of the omega. You know the optimal value of the omega is what? 2 divided by 1 plus this one. And the spectral radius Tj you just have is what? Is 1 over √2, and you make it square, and when you simplify, you will get this one. This is a spectral radius here, and you get the omega value, and this is also the correct one because omega value should be between 1 and the 2 we have here now. Here I calculate to find Tg, and you know what is the formula of Tg, and the formula of Tg is what? If you remember, it is, I think, L plus D inverse into U, and this should be multiplied with a minus. This is the formula. But you don't need to do this long work. You directly do what? Directly do, you know the value of Tj, make it square, and that give you the value of Tj, inshallah. And you can see, we know what is that Tj, is this one. When you square it, it is become what? Half. And when you calculate here, this is a spectral radius is half. So no detail. You see, this is I mentioned here. So you directly you can find out from Tj. No need to calculate this one unless I mention it, do it separately, then you have to do okay. And what is the third one and the last one? The third one and the last one. Where is I didn't give here. And the third one in the last one is what, please?
Doctor,
Yes.
we can use this process if two conditions satisfies. One condition diagonal and positive.
Definite. Yes. But you can also use this condition. If it is not positive definite, it's not tridiagonal, but this happened. But this happened, and this is what? If the spectral radius of Tj range is between 0 and 1, then you can use this one also here. What is your T omega, please? T omega formula, I already told you. What is the rho of T omega? Rho of T omega equal to what? Omega minus 1. What is your omega? You just calculate 1.1716, and which is equal to what? 0.17 That's the job. And now, my second part of the question was, show that SOR method converge faster than Jacobi. Yes, it is, because what is the spectral radius of SOR method iteration matrix? It is 0.1716, and we know this is less than what? Gas idle. And what is the gas idle we have? Is 0.5. And 0.5 is less than what? 0.7, I think. 70. And smaller the value of rho of T, faster the convergence of the matrix will have here. Is okay? This is the same thing. I give another example by 4 by 4, but in exam, of course, I cannot give you 4 by the 4 we have here now. This is, I solve the system here now. And I say that compare the convergence of the Jacobi and Gauss-Seidel and SOR iteration method for this given system. And then I say use the faster convergence method to find the second approximation. Yeah, this is a way problem given in the exam, but should not be 4 by 4. It should be 3 by 3 in the exam here. So this is a good example, please. So you have to do the same way which we did before. You need to find out always Jacobi iteration matrix. And when you find its the eigenvalue, and eigenvalues are this one. And then you have to take which one is the maximum. And the maximum is this one. And this is less than 1. Then you have to calculate directly from the condition which I give you for the TG, also less than 1 and 1.6 here. And then you have to calculate what? Optimal value of omega, which is, inshallah, you will get that one. The same way which we did before, previous example. And then you find out the directly from this here. And then you can show the spectral radius of omega is less than the spectral radius of TG is less than TG. Smaller the norm, rho, spectral radius, faster the convergence of the matrix we have here now. Then he say, use the faster convergence method. And of course, the faster convergence method is SOR method. Then I use SOR method for this case, and I find out the two approximation, the first one and the second one. You already know where is the SOR method. This is the SOR method formula we have here. This is your third iterative method here. But sometime in exam, like this example I give in the before, where is, I give here something here, 2 by 2 matrix. Definitely, if I give only SOR method in the exam, I will give you 2 by 2 system only. Where is that example I give here? No, go up. Come on, where is that one which I calculate the, yeah, this is the one. This example I can give you here. I can also give you, last time about 1 year back, I give A is this one, and also I give the B, something like, so let's say B is your is 1 and 2 we have here now. Then I say this one, that use, I gave this one initial approximation also. The initial approximation, for example, is 0, 0, right? Then my question is, use SOR method to find out the second approximation. How can you find out this one? Definitely you have to do the formula. You have to calculate what? The only things you have to calculate is omega. And you know, to calculate omega, what you need? You need the spectral radius of Jacobi iteration matrix, because we have to use in the formula to find out the omega. So directly he can give you to find this one also. And also, one time I give the question in the exam here. You remember I give you the error formula, error bond formula of the iteration matrix. Which example I give where? I just forget now. This is the error bond formula for the iterative methods. The only difference is what? T. So I can ask in the exam here that find the error bond for the case of SOR method. So SOR method, what do you need? You need TW. And you know TW, you already calculated in this example, which I show you here. This TW you have to find out. This is a TW you have. So this is the 3 version I mentioned you. Any one of the version can be given in the exam, inshallah.
Doctor.
Yes.
I have a question about omega.
Yes.
The last step, how can we find the omega? You said the calculator, we use the calculator?
No. You know how to find omega. The omega formula, I give you the optimal value of omega formula. Where is that one? Theorem 1.36. This is a way you can find omega. Only this is a way, no other way. So only you need to calculate what? The iteration matrix for the Jacobi, and then take its spectral radius, and then use the formula this one. Is okay?
In the same example, you did the same. I mean,
Yes.
you was, yeah.
The same thing, exactly the same thing here. To find omega here, but this example which I solved where 2 by 2, I myself give the value of omega. This is for this example 2 by 2. I give myself to the omega, so no need to calculate by yourself. This is 1 year back. I give this example myself omega.
Okay.
But I say find the error bond. So it's mean, how can you find the error bond? You need TW. You have to calculate TW from here. And only you have to remember this formula for the TW. And omega, no need to calculate by yourself, is already given by the teacher. So we can have here now. Directly you can have.
Yes.
Is okay?
Yes, okay.
So you can use, as I told you, this 3 condition when your A is a positive, definite, and tridiagonal to find omega here. But you can also find omega if this condition is true. And the condition is what? The value of the spectral radius should be between 0 and 1. If it is not, then we have a problem here, because this will be the big value. And big value mean greater than 1. So 1 minus greater than 1 is a problem in the square root. We never have a negative inside here. Therefore, we can say here, if the range is this one, if the range of spectral radius is between 0 and 1, then you take the power, it becomes more smaller now. Then I give this example for the things here. And we finish the third iterative method. So we have a 3 iterative method. The Jacobi, we make small change in it. We have a new one called Gauss-Seidel. We make a small change in the Gauss-Seidel. We have a new formula, which we call SOR matrix we have here. And this is the matrix form of SOR method. You know how to find out this one. TW formula is this, that you have to remember. And the CW formula is this one. The last topic of our this first portion, it is error in solving the linear system. Very simple topic we have here now, but it's a very good one here. You remember that one here, when we solve the linear system, especially with the help of the iterative method. And I told you the iterative method will give you some approximate solution. Direct method, we can have a chance to get the exact solution of the linear system, but in iterative method, we will get approximate. Should be very good approximate, but must be the approximate. And when you have the approximate solution, it means error must be there. Because if you are exact and approximate, which we cannot use logically, that they are equal, then we can say the error is 0 here. Of course, approximate is very, very close to the exact, but not equal. So therefore, there must be some error in solving the linear system. What we will discuss here, there are some reason also, even you are using the good method, but still your error increase. And when this error increase is depend on the conditioning of the linear system. So up to now, we never discussed conditioning of the system. Up to now, what we check only? We check our system should be non-homogeneous, system should be simultaneous, system should be non-singular, and alhamdulillah, we have a unique solution. Now we have to check an extra job here in this topic, and we have to check the conditioning of the linear system. What does the conditioning mean? What do you mean by condition in the simple language? Condition mean the good health and not a good health, right? Or we can say the well condition, and well condition mean is a healthy one, right? Well condition, and opposite of that one is what? Of course, we call it ill condition, sick, right? And you remember that one here. If someone is sick, of course, he will not do the good things as compared to the other one who is in a well-conditioned care. So the same thing happened here in our case. We have to check here before we solve the system. We have to check the conditioning of the system here. Our system is a well-conditioned. Alhamdulillah, we will go for it and we solve the system. And we will get a very good approximation. Even we use some ordinary methods, numerical methods. But if your system is ill-conditioned, an ill-conditioned system you are dealing with, ill-conditioned system is also non-singular, but non-singular only give you the unique solution. But he never mentioned you the is a is a good approximate here. So ill-conditioned system, even you use a very, very good numerical method, but you will never get a good approximate solution here. So that's the things we have to discuss in our this topic, which we call here, that we have to discuss the ill conditioning of the system. For this, we introduce one of the very best vector, which give us a close look on the conditioning of the system. It's called residual vector we have here now. And what is this one here? Is R equal to B minus AX star, B original, A original, and X star is a approximate solution we get with the help of some numerical method. What is your original system, please? The exact system or original system is what? Your exact system or original system is this one. A given, B given, and we have to find out approximation of what? This exact solution, which we call is X now here. Can I write this one in this form? B minus AX is equal to what?
0.
Is a 0 here. So now if you can compare with this vector and this equation, this be exactly same. Minus, we have a minus here. We have A and we have A here. Here we have X star, which we call approximate solution. We call, this is the things I call it here. We call approximate solution. And how we got approximate solution? Alhamdulillah, we discussed many methods now. 4 from the direct method, 3 from the iterative method, any method we use here. We find out. So, and this is the approximate solution of this one. What is your R should be, please? What is your think if you compare with this one and this
Should be
equation?
0.
Is, should be?
0.
Not 0, but should be very
the
close to
Yes.
the 0. 0
Very close.
only possible when we deal with the exact. Here we are dealing with
Similar.
the approximate.
Approximate.
Yeah, so that's the things we can have here. It's mean if this vector is very small, and when your vector is small, what does this mean? This mean your error
Well conditioned.
no. If we say R is small, it means the error should be small. Error is what? Exact minus
Approximate.
approximate, right? This should be what? It should be small. When we say R is small, it means we have a very good approximation of the exact solution. And then when we say R small, it means error small. If these things happen, we are dealing with the well-conditioned system. But in many systems, million of the system, we have the cases when R is small, but the error is a very big error. It means something wrong. Is wrong not in the solution, is a wrong in the problem in the system itself. And this problem in the system mean your system must be ill-conditioned system. An ill-conditioned system should not be solved. If you solve the ill-conditioned system, generally you waste your time here. You understand my things now, right? That's the things we have to discuss. This is called the relative residual vector we have here now, which we taqsim by the B num here. We have this case now. We have this very simple system. The exact solution of this system is, 1, 1. And you can put here 1, 1 here. Let's try use one of the best method among the 7 methods we discussed here, and we got approximate solution is this one. Now you can see when you put 3 here, x1 is 3, x2 is 0. So we have 3 equal to 3, alhamdulillah. And if you put here 3 here, you have 3.003, which is a good one, approximation 3.0, which we say is a very good way in the system wise here, but this is wrong here because we have the exact solution is 111, and approximate is a very bad approximation we have. And you look for the error. Error is what? This minus this, which is what? 2, I'm right? You know what is the L infinity norm of a vector? L infinity norm of the vector is the largest element in absolute sense. So 1 minus 3 is at minus 2. 1 minus 0 is 1. So minus 2 and 1. Which one is the maximum in absolute sense? Is a 2. So we have a big error. And when you calculate R, your R is, you know the formula for R is a B minus AX squared. B is given 3 this, A is given 1 this, 2, 2. And X star is given this. When you multiply, inshallah, you will get this one here. And what is the L infinity norm of a vector? L infinity norm of a vector is a maximum value in absolute sense, which is this one, and which is very good one here, which is a very small number. R is small, but error is very big error. It's not close to 0. It's a big error. It means something wrong with the system. And the wrong with the system is this system must be the ill-conditioned system. So whatever the method you will use here, you will never get a good approximate solution for that case here. To check the ill conditioning, we can have a many rule here, because here we check ill conditioning by solving the system, which is not a nice idea, but this is the original definition we have. Now we need some concerned result which give us the idea of the conditioning of the system without solving the system here. And that we will discuss here, the ill conditioning of the system here, please. There are many here, but I give the example, many example here. And this is a formula which give us the idea of the conditioning of the system here. And this is a special matrix we have, and that called the condition number of a matrix. And what is the formula of the condition number of a matrix? The condition number of a matrix is, formula is the norm of A into norm of A inverse. And the condition number of a matrix is always greater than equal to 1. So this is the range of the condition number of any matrix we have, greater or equal to 1. This is the starting position, and Andrew is infinity also can be. Now, with the help of this condition, we say Q of A always greater than equal to 1. So we can say here, if the value of K of A is very close to, if the value of K of A is close to 1, then we say A is well conditioned. But if value of K of A is greater than 1, that means very away from 1. It means your A is ill condition we have here now. Now the question is always a student asks me, when we say the value of K is close to 1, which number we can say close to 1? Here we cannot fix any number. For the sum system, 3, 4, 5 also give you a very good the conditioning of the system here. But generally, when we say ill-conditioned system, the value of R, value of K of A is very big one we have here now. Value of K of A is the very big one here. Like, for example, we are given this matrix. This is a matrix we have here now. And it's inverse. You use calculator to find this one. So what is the L infinity norm of A, please? L infinity norm of A is what? The 5.99, right? Right? 5.99. Because the second row is a maximum here. And what is the maximum here is that this one we can calculate and we can have here now. And this is, this is close to 1. No, wallah. It is not ill, it is already dead. We can say it's dead. Your system is dead here. So this is the things we can have here now about the ill conditioning system here. But we can have many ways to check the ill conditioning here. The one way, as I told you, by the condition number of a matrix we have here, which is if the condition number of a matrix is close to 1, we say is a well conditioned, otherwise ill conditioned. Also, you can have another way to check. You see the matrix A is this one. The element of the matrix A are very small, 1, 2, 2, and 3. But when you find inverse, they are very big. It means something wrong. And the wrong is your A original is ill conditioned. And also there is also the other condition we can say here for the ill conditioning here. I mentioned here in this example, we have, this is a system, right? Your X, A is what? 1, 1, 3, 3, and 1, and this is your B. And when I solve this system, okay, the system has no solution for this case here now. But what I did, in place of 1/3, I use is a 0.3, right? When I use the 0.3, my solution is this one. You can check this is 2 by 2. Now what I did, in place of 0.3, I just change it. I use 0.33. And you can see the change in A is very small because only I change 0.3 to 0.33 and my solution will completely the change. This is for 0.3 and here this, and then I change to 0.333 and like this one. And you see the solution is this one. It means something is wrong with the system, and the system wrong always mean the ill conditioning system we have. Same thing I did here for the change in the right hand side. This is my new system. There is no change in the A. I make small change in the B here now. With this B, you will get this solution, right? Now I change B into this one, and you see the change is very, very small. And this small change will change the solution here. And this is not a big change here. It means this system is, alhamdulillah, this system is okay we have here now. Stable or well-posed system we have here. So this is another way. If we make small change in A, but we have a big change in the solution, it means something wrong with the system. Or we make small change in B, and there is a big change in the system, it means something wrong with the system, and that we call it the ill-conditioned system. But if we make small change in A or in small change in B, and there is no big change in the solution, it means you are dealing with the well-conditioned system. This is another way we can have here now. This is the scaling I give here. For the case of this one, I give some example for that case here, please. Many example I give to find out. You see, your matrix is almost singular, 0, right? But you can see it is a very well conditioned matrix because this condition number of this matrix is what? Is a 1 we have here now. This is the things we have here. If we cannot check what value of k we should have here now, it is close to 1, we say, either 1, 2, 3, but how long we can go, that is no formula we can fix it here. But this is another way to check your system is ill or well conditioned, and that we have to check by relative error here. And this is the things we have to check. K of A, you know the condition number of a matrix. R is a residual vector we have here, and the B is the right hand side here. If this right hand side calculation will give you closest to the 0, it means you are dealing with a well conditioned system. If you have a big error, if we have a big value here, mean 0.5, 0.9, 1 point something, it means something wrong, and wrong is your system is ill conditioned system. I solved this example. I prove it here now. I give this example also here. This is also the example I give here, 3 by 3 here. And I say here, discuss the ill conditioning of the given linear system. So how can you do this one? You take the A of this one, and the A, inshallah, when you find out, it will give you this. Then you can easily use calculator to find out A inverse. And then what is your L infinity norm of A? The first row is 3, second row is 5, third row is 4. So it's mean L infinity norm of a matrix is the 5. A norm is A inverse is this one. The first, what is the first row? 3. What is the second row? 2.5. What is the third row? 4.5. So we have A norm, L infinity norm is this one. And we can have here K of condition number of a matrix, which is not close to 1, is away from 1 here. But we have the system is ill conditioned. You can directly say here. This is the first part of the question. And the second part, he say, if x star equal to this one, with the approximate solution of the system, find the R and its vector. And you know the formula of R is this one, B minus A x star, B given, A given, x star also given by the teacher, which is this one. A is this one, B is your right hand side, 1, 0, minus 1. And then you can find out this is the residual vector. And what is the L infinity norm of this one? The maximum value, maximum element in the absolute sense, which is what? Is the 0.07. This is the things here. And what is the last part? Estimate the relative error. And the relative error I give you is this formula. This is the relative error here. So you already have calculated K of A. You already calculated R. And you calculate, what is a B norm? What is a B norm?
1.
1. B norm is a 1. Yes, is a 1. So we can have here now, B norm is a 1. And this is your K of A. This is your R. And that is the relative error. And this is a very big error here. Why this is big error? Because the given system was the ill-conditioned system. There are 3 cases for the ill-conditioned system here, which I give you here. Generally, in this start, I give the proof to show the proof, but now no one give me the proof for the last 10 years, so I just left. Only you have to give me the final answer here. Then I say here, if there is a small change in the right-hand side, and the small change in the right-hand side is B plus delta B, And my question is, what is the change in the solution? And the change in the solution when you calculate that formula, you have to remember that one, please. This is a formula is what? When there is a small change in the B, what is a small change in, relative change in the solution? This formula you have to remember. Second case, when there is a small change in the coefficient matrix A, what is the relative change in the solution? The relative change in the solution. This is slightly big one. You have to remember that one. And this is the change in the solution. And the third and the final case, if there is a change both in A and B, small change in A, small change in B, what is the change in the solution? And change in the solution is this one. This is the question I can give you in the exam, please. Like this one here. This is I give A and B. Then I say, this is your A. The first part, discuss the conditioning of the linear system, which is very simple one. You know, you are given A, you have to use calculator to find A inverse. And then you find out here, K of A. If K of A is close to 1, we say well condition, otherwise we say ill condition. The second case, he say, if there is a change in B. What is your B? Your B is what? 1, 1, and 2. And I say there is a change in B is this one. So what is the change in B here now? You have to calculate delta B, and delta B is what? 1 minus 1, 0. 1 minus 1, 0, 1.2, 1.9, and 2. This is
1,
minus 0. So this is the second case. The change in A, this is your A, and change in A is this one. So only this part is changed to 1.99. So you can find. And the second part, third part is there is a change in A, and there is a change in B. What is the relative change? So that's 3 formulas you have to use here, and that I use here now, please. And you can calculate easily the value. This one. This is a change in the B. This is a change in A. And this is the last one, the change in both A and B. This is the things we have to do here now. Now, sometime here is, as I told you, we have million of the system, they are ill conditioned. And I told you, if you want to throw the system ill condition is the better, but sometime is what we can do if your system is ill, and of course, as I told you, ill conditioned system give you the bad approximation. But there are methods available which can improve the accuracy, which can improve your approximate solution, which I discuss only one method here. And that method, we call it the method to solve the ill conditioning system. And that method is called the residual corrector method, or sometimes we call iterative refinement methods. This method will do what? Make your poor approximation of the ill conditioned system better and better here, and coming closer and closer to the exact solution here. This is the beauty of this method here. And very simple method is this one. We are given the original method, original system, which is ill-conditioned system, definitely. And we say, we find its approximation. We got its approximation by using any method we discuss. And we find X1 here. And this X1 is the approximate solution of the ill-conditioned system, which should be very bad one. Then what we have to do here, we have to define new vector in that sense here, and that is a new approximation in the ill-conditioning system with the help of this y, that you have to calculate y. And how to calculate y? You have to solve the linear system ay equal to r. And how to solve this system? Very simple one is a simple gas elimination method you use. So in the simple gas elimination method, what you do, please, if you remember that one, you use what? A augmented matrix, right? With the B, and you convert into what? U and a C. And then you use what? Ux is equal to the unique solution. So in place of B is what? R. And you know what is the value of R? R is B minus A X star. X star means approximate. An approximation is given here. So it means first you have to calculate R by this formula, and then you solve the simple gas elimination. In place of X, we have a Y. And when you have a Y, you put here, this is the original, and this is the new one. And with the addition of this one, this we have a new approximation. And that is a new approximation of the ill-conditioned system, which is better than the original given by us here. And if it is good one, we stop here. If it is not, we use one more time here. We continue like this one here. And like this one, I give the one simple example. We have an ill-conditioned system, this one. And he say he has the exact solution is this one, but the approximate solution we got is this. We want to make it improve. So what we do, we have to calculate R. What is the R formula? It is B minus A multiplied by X1, and we have R. We solve this system to find out Y1, and Y1 will be this one here. So what you have now, please, you have X1, which is given by the teacher, plus Y1, you just calculate by yourself. And when you do this one, what is this one? This is a exact solution you have just in one iteration. This is called the residual corrector method we have here. A residual corrector method we can use to find out the better approximation of the ill conditioning system, better approximation of the ill conditioning system we have. Any question now, please? Then in the end, I discuss some application for electrical, or you can see, look for that one here. I give the application some in the traffic flow, or like this one, different. And in all your things here, how can we convert into the linear system? And when we convert into the linear system, then we can easily solve it. And that's, as I told you, about 75% research in the different field of engineering. They convert their problem into the shape of the linear system, and then they can solve it easily by using the numerical method we discussed here. This is our first portion of the syllabus. We finish that portion now. Any question you have now, please? And I think we go for the first midterm exam First, how many? 2 midterm we decided, I think.
Yes.
So first midterm exam, we will go
Yes,
for,
doctor.
first midterm exam, we will go for up to this one here. And I will try, because there is my exam on 23rd of March. It is in the 10th week. We go for the same day. If the room is available, we go for our exam on 23rd of March. In the 10th week, it is Tuesday from 7 to 9 o'clock. Face to face, please. Is okay with you?
Excuse me, Doctor.
Yes.
On Tuesday, we have another lecture.
On 23rd of March?
Every week, actually.
What time you have a lecture?
From 7:30 up to 9:30.
Which course is that one?
EE 546.
There's from electrical you have. Then it is a problem for me, because I have to take care of all. Let's say I discuss with the department, they give me the alternate date. What date you want?
I think same today, Monday.
Huh?
Monday, 22 of March.
Monday, 22 March, right? So from 7 to 9. Let me check here. Because the problem is, during that day, there are many exams that sometimes the room are not available. Let me discuss tomorrow, inshallah. Okay.
Okay.
Still, we have a plenty of time for that case. And we will, inshallah, discuss about, don't worry about this one. As I told you, and I think I send you the file, that you have to make the computer programming for simple gas elimination, partial pivoting, and complete pivoting together in one file only. And you have to only mention here which one we are going for, that one, and then that part of the file will be active. One file, the programming file, which consists of 3 programming: the simple gas elimination, the partial pivoting, and the complete pivoting. If you did this one very nice way, you can have more than, you have a 15 marks, I think I give you the computer assignment, 15 marks, 5 for the talk, 20 for each midterm exams, become 60 altogether. So if you do this one, you have a plenty of time now, and you can make it program in MATLAB or whatever the language you have here now. And you pass on to me week before in the USB by taking some different example and show to me, please. In the USB, right? And also the talk, you have to choose, as I told you, the talk consists of 4 or 5 pages of the PDF file or PowerPoint here, and you have to choose any topic. For example, if some student using LU decomposition by Dolittle method, some student using simple gas elimination method, some student using positive definite matrix, some student using non-singular matrix. You have to define some in your word with the 4 or 5, like not 5, the 4 is enough page, either in the PowerPoint or in the PDF file, and you have to put together with the USB to me here, please. Week before the final exam.
Excuse me, Doctor.
Yes.
Actually, we didn't receive any email since 6th of February.
No, what I do, I will send you this complete chapter now, right?
Okay.
the just, it has, I have is the 145 page. It is from the start, right?
Okay.
I will send inshallah up to this one here. I hope it will come in the file here. It's not a big file here. I will send this one here. So it's mean I finish all the material with you, right? And recording lecture already I will send you. The recorded lecture you also already you have now on my Google Drive. Yes?
Yes,
the
yes, recording we
Yes,
can.
doctor.
Yes, okay.
We don't have the lectures, the PDFs.
No, PDF. I will send you today, inshallah, inshallah. Today, this complete file, right?
Yeah.
So it's
Yes.
already corrected, some mistake already corrected here, so don't worry about this one.
As well as the assignment, Doctor, please.
Yes. Also, I mentioned assignment.
Yeah, I mean MATLAB.
What?
I mean the email regarding the.
Okay,
Well,
don't worry.
Yes.
I will write the mail and I mention about this one. Okay, any other question for this one? Then I give you the small introduction of the other part of that one. And then inshallah, we continue next time here. Let me take we have math 550. So we finish. This is, I think we have yes, that's the second portion we have here now, which I call is the chapter number 2. As I told you, this chapter or this part of the syllabus behave like application of the first part. What we did in the first part, this make our first part more easier to understand here. So we take as the application of this one, and this also play a very important role in the engineering problem or solving the differential equation, or in the other sense here, we call it the eigenvalue and the eigenvector. As I told you, we will go now totally opposite what we finish in the first part here. And the first part, you remember, our system was simultaneous, right? We keep this one here also, our system should be. But generally, we will not discuss system. We will discuss only the matrix here, right? And, or okay, we can discuss the system, no problem. So we have the simultaneous system, which is the same we discussed way before. And the second point is different. We discuss non-homogeneous. Here we will discuss homogeneous. That the first part we discuss our system, because that's the important things we can have here now. If I write here, in the first part of the portion we have here now, we deal with the homogeneous system with the condition, the determinant of A not 0, and then we have unique solution. But if your determinant is 0, we will never have a unique solution. We have a infinitely many solution or no solution. Now, what we do here in the case of our new part of the syllabus, which we call is the eigenvalue and the eigenvector, our system must be homogeneous. And homogeneous system mean your right hand side must be equal to the 0. And the other thing, your given matrix you have to convert into the new matrix, and that new matrix must be singular. So it's mean your system should be homogeneous, and your system should be singular. No chance for the non-singular system. We will discuss here. And you remember one thing here, if your system is a non-homogeneous system may be consistent, may be inconsistent. Consistent mean unique solution or many solution, and inconsistent mean no solution. But your homogeneous system always have a consistent. No chance we can get no solution in the case of the homogeneous. Either we will get the unique solution or infinitely many solution. Since your system is, in this part, your system is a homogeneous and it is singular, it means you will always get the infinitely many solution we have here now. Just shortcut is here now. This is a main equation for the second part, which we call the eigenvalue problems. And we are given a square matrix, and we have there is a vector, non-zero vector we have here x. And if we have this type of equation, which we call in some sense is a linear system. This is a linear system in x again. And that linear system we call the new problem, which we call the eigenvalue problems we have here now. If you look for this one here, what is the difference between our previous linear system equation and this one here? Here we have one extra thing, which we call the lambda. Of course, the b, we don't have b here in this case because we have the right-hand side is 0 in our sense here because we are dealing with the homogeneous. So we have to deal with this equation or system, and this system we have to deal with the two things. We have to find out lambda and the x. Lambda generally we call the eigenvalue of a matrix A, and x we call corresponding eigenvector of the A we have here now. And this is the things we can have here now. We have to start with the math system. Ax is equal to the lambda ix, because your lambda is a real number. So I have to take on the left-hand side. Therefore, I multiply with a matrix, unit matrix here. And then we can take the left-hand side here. And that's the things we can have here now. A minus lambda I, x is equal to 0. This is a shape we have our system in second part. And that shape, if you can look for this one here, this shape is a homogeneous system. And the homogeneous system, as I told you, always have a two solution. One solution which we call is a unique. If unique solution, the unique solution we call trivial solution, and trivial solution mean for any unique solution, the jawab must be 0. It means all the element of the vector x should be 0, which we are not interested. We do the lot of job, and in the end we get the jawab 0. So therefore we never interested in the unique solution of the linear system, and we are interested in the non-trivial solution. A non-trivial solution mean we call it the infinitely many solution here. So as I say, we have to play with this equation in the two parts here. In the first part, we deal with A minus lambda I, which is a matrix for this one. And as I told you, this matrix A minus lambda I must be singular. If your original A is given non-singular, but this lambda always make it singular, right? This is the beauty of the lambda we have here now. So we have to deal with the two part here. This is, I mentioned you, the trace of the matrix, because this is very important matrix we have, especially when we are dealing with the eigenvalue of a problem, because I told you the trace of a matrix and some of the eigenvalue must be equal. And we know what is the trace of A. Trace of A is the sum of the diagonal elements here. So this is the first definition you have to remember. This is, I give some property of the trace here, which we are not very much interested. And this is the things we have here. So we divided over the first part, how to deal with the finding the eigenvalue of a matrix. The eigenvalue of a matrix, we have to deal with this one. So as I told you, we have to find two things. One is a lambda, which we call eigenvalue of a matrix. And then we call the second thing is eigenvector, which is a solution of the homogeneous system. So this is the first case we have to deal with. Our lambda, we have to find the determinant of A minus lambda I must be equal to 0. This will give you the polynomial. And after we having the polynomial here, this is, I give the example in the different sense here now. Show by that one here. This is also, remember this one here, which I give you the formula, sum of the eigenvalue and the trace must be equal. And this is also second formula you have to remember, please, that if you multiply all the eigenvalue, this will give you the definition of the determinant of a matrix. If you want to find the determinant of the matrix, so how can you find the determinant of the matrix? Multiply all the eigenvalue together, and that give you the determinant of the matrix. And now you can see from this definition, if any eigenvalue is 0, it means determinant must be equal to what? The 0. It means now you have a new definition of the non-singular and singular. If all the eigenvalue are non-zero, it means your A must be non-singular. If any eigenvalue of a matrix is a 0, then that matrix guarantees singular we have here now. This is basic things we have, which is not too much important things here. We have to talk about these things here, as I told you here. We have to start, as I give you this example, then we continue next time, inshallah. He said, as I told you, we have to deal with two things in this one. We have to deal with lambda and vector dx. Lambda is a real number, maybe complex, but we are not interested. We are only discuss the real eigenvalue, not the complex eigenvalue throughout our discussion. And X is a corresponding eigenvector we can find after finding the lambda, we can find here. So as I told you, so we have this two steps to do here. The first step will give you the lambda. And how to find lambda, as I give you the formula, determinant of given original matrix minus lambda I. This should be equal to 0. So you can have the value of the lambda. After you have the value of the lambda, then you find the second part of our question, and this means we have to find eigenvector, which we call X. And how can we find this X? With the help of homogeneous system, which we call A minus lambda I into X must be equal to the 0, must be equal to must be equal to 0. So we have to solve the homogeneous system. And when we solve the homogeneous system, as I told you, homogeneous system always have a two solution. One is a unique, another is infinitely many. And we are not interested in the unique. We will always get infinitely many. And you remember when we get the infinitely many solution, please. You know that one, the basic idea. When you get the infinitely many solution, when your simultaneous system become any student, please say even wrong, or if it's correct is a good one, wrong, no problem. When you have the infinitely many solution, you remember, as I told you, when you have if your simultaneous system become underdetermined system. An underdetermined system is what? You have less equation and more
variables.
You always have infinitely many solutions. So in this case, in this part, your simultaneous system, after you put lambda value, it always become the underdetermined system. And the underdetermined system, when you have, so you have the infinitely many solution for this case. Let's give you the very simple example, then we continue next time, inshallah. He said that find the eigenvalue and the eigenvector of this following matrix. So what you have to do first, you have to find A minus lambda I equal to 0, and we have, this is the things you have, A minus lambda I equal to this one. When you simplify this one, you have lambda equal to 4 minus 3 and 2. What is the trace? Trace of A is what? 3. And the sum of the eigenvalue is 3. So alhamdulillah is okay. Our eigenvalues are correct one here. No need to check another way. So we have a 3 eigenvalue. So for each eigenvalue, we can have the vector we have here now. First I put lambda 1 equal to 4 in our equation. In this equation, when you put A minus lambda Ix equal to this. So when you put lambda equal to 4, you have this one here shape. And now when you can have here this shape, so you can have this one. So you can see here, what is second equation give you? Directly give you what? x2 equal to what?
0.
0. And what is your first equation give you? x1 equal to x3, I'm right? And what is your third equation give you? x1 equal to
x3.
which is the same. So of course the same, we will ignore it. So how many equation we have?
You have 2.
2, and we have a 3 variable. So we already know x2. So x3 you can put here, as I told you, you can put any value of x3. You remember in the previous case, we can say x3 equal to t, t is any real number but not equal to 0. Therefore, as I say, you can choose any value of x1 or x3. You can, it's your choice. Therefore, we say, because the infinite many solution of you and other student may be not same, but no problem, because infinitely many solution mean is depend what you choose. For example, I choose here x3 equal to 1. When I have x3 equal to 1, I have x1 equal to 1 also. But one student maybe he not use 1, he use 2. So you have 2 and 2 like this here. So that is the infinitely solution corresponding to lambda equal to 4 now. And the second case, we choose lambda equal to -3 now. And when we put in a minus lambda xi here, and we have this shape now, if you look for this shape here, you can see here, your first equation give you what? x1 equal to -1 over x3. And here you have, what is the value of x2? You have x2 here somewhere?
Will be 0.
No, you cannot have a 0. x2 is not majud here, right? Because we cannot find x2 here. This example is a very simple. You have x2, 7x2 equal to 0, so it means you can find x2 directly. But in this case, your first equation never have x2 because it's already coefficient 0. The second, all zeros, and the third is x2 also. So it means you can choose any value of x2. I say x2 equal to infinity mean any value you can choose for here, 1, -1. But as I told you, my advice is always use the simplest one number, and the simplest number when you choose is the 1 here. And then we left here now, x1 equal to -1 over 6x3, and x1 equal to this one. And this is only possible when they have the 0 value. Otherwise, no chance they are equal. So you can see it's mean your x1 and x3 are equal to 0. And x2 equal to any number you can choose. I choose x2 equal to, because your vector, eigenvector, remember that one, your eigenvector should not be, this is a point, remember please, your eigenvector should not be repeat, and your eigenvector should not be 0, all the elements 0. If you have something like this one, it means it is the big mistake in your second portion. The second portion, remember that one. Your eigenvalue may be 0, may be repeated, but your eigenvector should never 0, and your eigenvector should never be repeated. This is a point, please, you have to remember that one here. So you can see what is your first eigenvector is 1, 0, 1. Good, alhamdulillah. What is the second one? 0, 1, and 0. Not the same here and not the 0 here. And then you do the last things we have here now. It's lambda equal to 2. And you can have this equation and you simplify. You can have this shape. And then you can easily from the second, you have x2 equal to 2 and x1 equal to this one. So now I choose here what? I choose x3 equal to 1, then I have x1 equal to -1, or you choose x3 equal to -1, then you have x2. So this is, therefore, as I say, your solution and my solution may be not same because it's your choice. Therefore, we call eigenvectors should be always infinitely many, the solution we have here now. And this is the things we can have here now. This is your third eigenvector. And for each eigenvalue, you can have the different the vectors we have. Any question, please, up to now, this one? Very simple one, not a difficult things we have here now. We are doing by classical method. Classical method mean by analytical method, by exact way. And of course, we will not do exact way, but I give you in the start, the basic idea, how to find lambda exact way, how to find eigenvector by exact way here. But of course, we have to use numerical method. Very soon, inshallah, we do that numerically to find the eigenvalue and the vector of the original given matrix we have here. Any question, please? I give this another example, and we have 3 eigenvalue. You calculated 0, 2, and 3, and you can see what is the sum of the eigenvalue? 5. What is the trace of A? Is a 5. So alhamdulillah, the things are okay. And then you can find easily the eigenvalue corresponding to this one. This is a good example we have here now. Let's say do this one and then we finish here now. We have find the eigenvalue and the eigenvector. So you find the eigenvalue, and eigenvalue are what? Lambda minus 2 power 2. So it's been repeating your, as I told you, your eigenvalue may be 0, may be repeated. Maybe they're different. In first example, eigenvalue was the different here. So we have 3 eigenvalue, 2, 2, and 8. So it's mean, what is the trace? Trace 3, 6, 9, and 12. So this is 12. So, okay. Now, when you have the lambda is repeating, but its corresponding eigenvector should not be repeated. This is the things point you have to remember. I told you eigenvalue may be repeated, but eigenvectors should not be repeated. So when we have this one lambda equal to 2, we have this shape, please. And it is repeating. And you can see if you look for the first equation, second equation, and the third equation, if we look, they are exactly the same. If you multiply last equation by -1, because right hand side is a 0, exactly the same. If you multiply first equation by 2, exactly the same. So it's mean we have to choose only one equation, because repeated we will not choose. So it's mean how many equation you have? One
equation.
And how many variables?
3.
3. It's mean we have to choose now 2 element by ourselves. Remember in the previously we say either we say x3, we choose or only one. But here, since we have a 1 equation and 3 variable, it's mean we have to choose any 2 of them here. And that I choose x2 equal to s and x3 equal to t, with the condition s and t should not be equal. If you choose x2 is 1, x3 should not be 1, should be 2, 3, something different here now. So we choose this one here, and when we choose x2 is s and x3 is t, we can easily find out the value of x1 is what? It is, you take on the other side, minus 2s plus t, x2 is s, and this, you have this one. Now what you can do, make your s term separate and t term separate, and you can do this one when you have this separate when you do, and when you add them, you get exactly the same. Now your eigenvalue or lambda is repeating 2 times. It's mean, but their corresponding eigenvector must be the different. So eigenvector are different. First eigenvector for the lambda is what? -2, 1, and 0. And what is for lambda equal to 2 is the second lambda repeated. What is the eigenvalue? 1, 0, and which is not the same we have. And third one is a very simple one. Your eigenvalue is 8, and you can put 8 into the equation, and you can have this eigenvector x3 we have. So therefore, please remember that one here. Your eigenvalue must be real, maybe 0, maybe repeated, maybe the different. But your eigenvector, never 0, never repeated. If you are repeated, it means it is mistake by you. If it is all element become 0, it is mistake by you. It should not be happen in our second part of the portion, the syllabus. Okay.
Okay. So,
Right. So we continue, inshallah, the more
inshallah.
detail next time here. Any question you have, please?